Ladies and gentlemen, welcome again to this celebration of the 75th anniversary of the founding of the Institute. So today we are also celebrating the centenary of Albert Einstein's Annus Mirabilis, and that is the subject, or subjects related to Einstein are the focus of most of the talks we've organized for today. In this morning session, 3 of the members of the School of Natural Sciences will be discussing the papers that he produced in that remarkable year of 1905, and one of the professors in the school will discuss Einstein and quantum mechanics. And it's now my pleasure to introduce the chair of the morning session, Professor Juan Maldacena of the School of Natural Sciences.
As Peter mentioned, we are celebrating the 100th anniversary of Einstein's papers. So in 1905 he wrote 3 very interesting papers, and we'll hear a description of these 3 interesting papers. The first speaker is Philippe Argyris. Philippe was an undergraduate at Harvard. He got his PhD here at Princeton University. And after holding appointments at Cornell, Rutgers, and the Institute for Advanced Study, where he was for 2 years, he became a professor at Cornell, and he's now a professor at the University of Cincinnati. And this year he's spending his sabbatical with us at the Institute, and we are very happy to have him here on sabbatical. His research focuses on the dynamics of strongly coupled gauge theories, of strongly coupled supersymmetric gauge theories, and he found very interesting phenomena, and some of which bear his name. Well, with you, Philippe Argyris.
Thanks, Juan. Okay. So, as Juan said, 100 years ago, young Einstein wrote interesting papers on 3 subjects. And he probably wasn't this young in 1905. I suppose I should have looked it up. But I'm not really here to talk about history, about which I really know nothing. I just want to explain to you some of Einstein's physical ideas in simple terms. So if I say anything historical, you should take it with a big grain of salt. He actually wrote more than 3 papers. He wrote 4 or 5, depending on how you count them, in 1905. 2 of them were on special relativity. The first, called On the Electrodynamics of Moving Bodies, was the one that laid out special relativity. And then a few months later, I guess, he published a short follow-up, I think a 3-page paper, called Does the Inertia of a Body Depend on its Energy Content? And this is the paper in which, this is the E equals mc squared paper. So, now usually special relativity is thought of as a revolutionary theory which upsets our notions of space and time. And, well, in the poetic language of Minkowski, written just a few years after Einstein's paper, I quote, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the 2 will preserve an independent reality." So this seems like pretty heavy stuff to come out of a paper with a technical and prosaic title like The Electrodynamics of Moving Bodies. But there's a good reason for this title. The electrodynamics of the title is the union of theories of electricity and magnetism, and it's a wonderful synthesis which, as Maxwell realized sometime in the 19th century, he realized that it also explained light. Light is not a separate phenomenon, but light is actually a traveling electric and magnetic waves, waves in those fields. So these waves in a vacuum satisfy some equations, Maxwell's equations. One of these equations, or one form of these equations, you can write as follows. Now don't worry, I don't really care too much about the specific form of the equation. All I want you to take away from it is that there is some constant velocity or speed that appears in this equation, c, the speed of light. It's something that you can measure, and it's about 300,000 kilometers per second. Now, that's just approximate. I'm not just cavalier with dates, I'm also cavalier with lots of numbers. So it's this speed that enters into Maxwell's equations, which is the source of great consternation. And it's what ultimately led to Einstein's papers. So what's the problem with having a speed in Maxwell's equations? Well, the problem is that Maxwell's equations violate the principle of relativity. Now, wait a second. You might say, I thought Einstein invented relativity in decades after Maxwell, but no, there was a principle of relativity long before Maxwell, going back at least to Galileo and Newton. So, I don't know when that was, but the principle states the laws of nature don't depend on how fast you're going. Okay? This is a familiar principle from everyday life. For example, an important law of nature says that you have to throw a peanut more or less straight up if you want to catch it in your mouth when you're sitting down. And I demonstrated for you, but there's a more important law which says that if I actually caught it, I would choke, so I won't do that. And this law doesn't depend on how fast you're moving. If you were in a jet plane, you still throw the peanut straight up. You don't have to hurl it forward at 600 kilometers an hour for it to keep up with your mouth, right? In fact, you don't need a jet plane here. You're sitting in these seats here, but these seats are moving hundreds of miles an hour if you think of them because of the rotation of the Earth, and even faster from the revolution of the Earth around the sun, and even faster from the sun moving around the galaxy, and so on. And yet, you don't notice a thing. I mean, I hope you don't. If you're feeling dizzy, it's purely psychosomatic, okay? So the point is that all that matters is your relative velocity to the objects near you, the objects that you're interacting with, is one way of saying it. And from this, it's a short, but as we'll see, basically wrong inference to deduce that there are no absolute velocities. But this is the way people thought about it. Everything is relative, or at least all velocities are relative. So then along came Maxwell's equations, and he has an absolute velocity, a constant velocity in those equations, the velocity of light, and this can't be right. If a body, here Galileo, is at rest, and through some electrodynamic process emits some light, it travels away from him at the speed c, according to Maxwell's equations. And now, if the same body was moving at some velocity v, right? Here we have Galileo moving across. We'll stop him for a second. Then, if we look, since it's only relative velocities that matter, it should just be that we'll see the velocity of the light that he emits. He thinks it's being emitted with speed c relative to him, but we'll measure it and says it's going at that speed plus the speed which he's moving along at, c plus v. But Maxwell says that's not right. Light, doesn't matter who emits it, only goes at this constant speed c. So this was a problem. Either relativity is wrong or Maxwell is wrong. Okay? So Einstein's revolutionary proposal was actually, from this point of view, quite conservative. He actually said both are right. Laws of nature don't care how fast you're going, and the speed of light is invariant. So he's also implying that there's some mistake in the previous reasoning which said that there couldn't be absolute velocities. So the point of his paper maybe is that if we're just careful about what we mean by velocities, how we actually think about how we actually measure distances and times and velocities, then there's wiggle room, and we can make these two principles mathematically consistent. So maybe the name relativity or special relativity is a bit of a misnomer for Einstein's theory. I think the really new idea is that something, the speed of light, is not relative, that at the core of relativity there's an invariance principle. So I haven't told you how this works, how these are reconciled, and the right way to do it would take a little too long, so I'll try to give you some vague idea. I think one way of saying it is that Einstein points out that you can keep the speed of light constant from all observers' frames of reference, no matter, in other words, no matter how fast the emitter is going, as long as lengths of moving objects or distances in those moving frames are foreshortened, are contracted along the direction of motion. And at the same time, their clocks tick slower. Time flows more slowly in those things. These sound like very weird statements, but they can be made very concrete about statements about actual measurements. So one way of thinking about this is to illustrate it with a Gedanken experiment. Gedanken experiments are experiments which you don't actually do, you just think about. So Gedanken's like probably German for low budget or something. So Einstein says, suppose we have a moving body emitting light. So here's Lorentz, our moving body. For the moment, he's stationary. He's in the same, or at least with respect to Einstein. But Einstein says, let's pretend Lorentz is now moving past us at a speed v. Or equivalently, Lorentz stays still, whatever that means, and Einstein's moves to the other direction at a speed v. So from Einstein's point of view, he sees Lorentz going by. Let's freeze him here for a moment. So the idea is that distances along the direction of motion get foreshortened. So Lorentz becomes nice and slim, and everything in his frame gets foreshortened. And so I should also say that in some sense, the light that he emits also gets foreshortened. And I should also say that the times his clocks slow down as well. I could have tried to illustrate that on the PowerPoint, but this is just a Gedanken PowerPoint. The idea is that with these rules, which I'm not going to write out their mathematical expression so you could really see that they're consistent, but with these rules, Einstein, when he measures the speed of light relative to Lorentz, measures a speed c minus v. So the speed of light in Einstein's frame is that speed relative to Lorentz, c minus v. That c minus v comes from this contraction of the lengths and the dilation of the times, plus the speed which Lorentz's frame is moving at. So the total speed of light, the actual piece light as observed in Einstein's frame, is still moving at c. We still have this, we still have relativity, but we manage to keep the speed of light, no matter how fast the emitter is seeing it, constant at a total value of c. So relativity still holds. From Lorentz's point of view, he's just standing still. The light, he's just as chubby as ever. The light is leaving him at a speed c. And this is completely consistent from Einstein's point of view. Einstein can understand why Lorentz thinks this, just because when he measures things, he realizes that, okay, Lorentz is thinner, but also all his rulers have contracted. So when Lorentz tries to measure his own waistline, it will come out the same as it was before, from Lorentz's point of view. And vice versa, Lorentz is standing still, but he sees Einstein moving past, and so he will think that Einstein has gotten thinner. So, well, I guess this means Lorentz contractions would not make some sort of marketable slimming scheme, right? Because even though your client, Lorentz, would look slimmer according to everybody, from his point of view, he would look just as portly as ever, and everybody else would be annoyingly thin. So this aspect that all these effects are just depend on relative motion, that it's all relative, sometimes leads to the idea that these effects aren't real, that they're just some kind of, I don't know, optical illusion, because they can't be made into a profitable slimming scheme, right? But this is wrong. We've agreed on how we measure lengths and times, and these are the result, and this is telling us what the results of those measurements are. There's not another definition of that everybody can agree on of what you mean by how you're going to measure lengths and times, which gets rid of these contractions, right? Or maybe more to the point is that it's not just illusions, it's not just all relative. There are real, in fact, striking physical implications of this. Many of these implications are illustrated when this subject is taught in the form of these Gedanken experiments, usually put forward as paradoxes, and they're great ways of understanding how the whole thing works and sits together in a logically consistent way, like the twin paradox and the barn paradox and so forth. But in light of the time, and also since I want to get to the E equals mc squared paper, I'll just describe one, maybe the most important physical implication of this, which is that it takes an infinite amount of energy to accelerate any body to the speed of light, at least if it started out slower than the speed of light. So I'm going to have to show you some formulas here. You can calculate in this scheme how much energy it takes you have to add to a particle to speed it up from rest in a given frame to a given velocity. Einstein calculates this in his first paper. He can do this because he has a theory, Maxwell's electrodynamics, and so he can just say, I'll use an electric field, I have a particle, and I will slowly accelerate it up to a speed v, and I can integrate up the total work that I did, figure out the total energy that I've added to this particle, and I get that the energy of motion, the kinetic energy of a particle moving at speed v, is given by this formula, mc squared times gamma minus 1, where gamma is some slightly complicated formula in terms of the velocity, and the speed of light comes in. And it's a very nice formula. When v is very small compared to c, you can see that this is very close approximately to the old classical, say, Newtonian value for the kinetic energy. But when the velocity gets very close to the speed of light, this factor blows up. Gamma goes to infinity. And so as you keep on trying to push in energy, no matter how hard you push, you can never quite get all the way up to the speed of light. So the speed of light is not only some invariant speed, it's actually the invariant speed limit, right? So, okay. So in his second paper, his E equals mc squared paper, Einstein proposed the following thought experiment. He says, let's just use energy conservation and try to see how, if we can compute how energies of bodies change if they go at different speeds. And so he thought of this experiment. Let's say he's sitting still and he lets off some light. He radiates some light. That lets off some energy. Okay, there's some energy contained in the light. Say the energy is L. So by conservation of energy, the amount of energy that he lets off in light is going to be equal to the decrease in the total energy that he possesses. Okay? So that's just conservation of energy. So nothing new here, nothing having to do with relativity, no one's moving. But now consider the same process, but if he's from our point of view, where he is moving at a speed v relative to us, like that. So you have to recompute this thing. Well, Einstein didn't know how to compute the left-hand side directly, the new change in his energy from our point of view, but since he has a theory of light, he has Maxwell's equations, he can just directly compute what if the energy of light emitted in a rest frame was L, then in a boosted frame, when it's moving by at velocity v, he can just compute what that energy is, and if the light is emitted in a symmetrical way, the formula he finds is gamma times L, where gamma is again the same factor which blows up as you approach the speed of light. So he says, well, on the other hand, the difference between these two energies is just the energy due to his motion, his kinetic energy. So taking the difference of these two equations, we'll learn that the change in Einstein's kinetic energy, delta K, is just given by the difference of these two equations, so it's L times gamma minus 1. On the other hand, he had already computed that for an object, its kinetic energy was given by this formula. So if its kinetic energy, when it emits some energy L in its rest frame, changes by this much, it must mean that its mass changes by a proportional amount with a proportionality constant, this c squared here. That's the equivalence of mass and energy. E equals mc squared. Actually, in his paper, he never actually writes this formula, which I found very disappointing. But the closest thing he says, this is a slight paraphrase, is the mass of a body is a measure of its energy content. If the energy changes by L, the mass changes in the same sense by L divided by c squared. This is actually slightly more precise than saying E equals mc squared. What might be more disappointing to you is that this famous result was found in such a sort of technical way by the virtue of close reasoning and mathematical manipulations. And, well, I make no apology for that fact. In the end, the physical world is a logical place. It's a logically consistent place. If you have a theory in which some statements seem intuitive or obvious, and other ones follow from them logically but don't seem obvious, it doesn't matter as far as nature is concerned. They both hold with equal force. It just so happens that E equals mc squared in special relativity is one of these non-obvious statements. But it's just as, if you accept the rest, you need to accept this. Thanks.
The next speaker is Graham Cribbs. He did his undergraduate in engineering in Toronto. Then he did his PhD in Michigan. Then he has done research at Carnegie Mellon, Wisconsin, and then the Institute. And he has concentrated on understanding the origin of mass, that is to say the origin of electroweak symmetry breaking, and the nature of dark matter. So with you, Graham Cribbs.
So the organizers of the session asked me to talk about Einstein's paper on the photoelectric effect, which is what I'm going to do today. It was in fact his first paper that he wrote in 1905, in March of 1905. I need to give you some history to give you an understanding of why it is that he came to write this paper and what its consequences were. So in 1859, Kirchhoff proposed an idea of a particular type of body called a black body. A black body is an object which absorbs all light and turns it into just thermal radiation, just into heat, if you will. Okay? Kirchhoff thought this was an interesting result because if you put a black body in thermal equilibrium with radiation around it, he realized that the only property of the radiation that would be in equilibrium with the body, the only thermodynamic quantity associated with this would be temperature. In particular, the spectrum of the radiation should only depend on the temperature of the body, of the black body itself, if it is a pure black body, one that converts all radiation into heat of the object. So in 1859, this was his proposal, this is what he had understood from thermodynamics, and then he sort of challenged the physics community at the time to say, okay, so if this is right, theorists, you should go off and derive the spectrum, and experimentalists, here we go, experimentalists, you should go off and measure it, and then we'll come back and meet and see how we did. Okay? And this is the standard way in which physics is done then and now, is exactly like this. Well, what he didn't realize is that Physicists actually spent the better part of 50 years working on exactly this problem. Okay? And there was progress, but it was slow going, and you'll see why in a second. On sort of both experimental and theoretical front, Stefan and Boltzmann, Stefan an experimentalist, Boltzmann a theorist, realized that the power that is emitted from a black body is proportional to temperature to the fourth power here. Yeah. This is the total integrated spectrum of radiation that would be emitted from a black body. This constant, of course, is now known as the Stefan-Boltzmann constant after its inventors. So this was one piece of progress in the 1800s. By 1893, Wien had written down a spectral density, something that he basically just guessed. And again, this is not unlike how physics operates. You often just simply guess a result and then follow its consequences. He guessed that the spectral density took this form, okay, in terms of the frequency and the temperature of the body. Notice that it has no characteristics of the body itself. It doesn't matter whether it's iron or gold or air, doesn't matter. If the body is truly a black body, then it only depends on the temperature of the body, and the actual spectral density itself had the form of going like the frequency to the third power out front, and then an exponential of the frequency divided by the temperature with some positive constants here, A and B, that had to be experimentally determined. The consequence of this exponential with a negative sign here meant that initially the frequencies would grow as you go higher in frequency, but then eventually they get damped by this term, and it always wins out. Well, at the time, in 1893, Wien's law satisfied all of the experimental data, okay? But the subtlety was that the only experimental data that had been done at that time had been at high frequencies, at frequencies where, when you plug those into this formula here, you find that actually the exponential is dominating. Okay, now that may seem like a sort of a subtle technical point, but you'll see that was a crucial fact to be able to go further in this progress, in this game. By October of 1900, things were beginning to change. Actually, in earlier of 1900, there had already been hints that that Wien's law didn't work quite as well as he had hoped, or quite as well as experimentalists may have hoped. But by October, it was very clear that his law was not valid when one takes into account measurements at low frequencies. Here's a plot of the data that actually came out from this work in 1900. So what's plotted here is the intensity of the radiation as a function of the temperature of what was, as best could be constructed at that time, a black body. Okay? You forget about all the lines except for the dashed line here and the points that you see coming down the plot. Okay? The dashed line is Wien's law, and the points are what the experimentalists had measured using these new low-frequency techniques that had only been developed just a couple of years earlier. So you can see that they don't agree. They certainly doesn't have the same shape and doesn't look like it fits Wien's law. Well, as it happened to be, a physicist by the name of Planck had one of these experimentalists over to dinner in October of 1900, because they happened to be at exactly the same institution. And the experimentalist had emphasized one crucial fact to Planck. The experimentalist had said, well, we go and measure this data, and what do we find? But we find that it looks like it's proportional to temperature in the low-frequency regime. The spectrum of radiation that you get at is proportional to temperature in the low-frequency regime. With that one fact, Planck, within a matter of a day or maybe not more than a week, guessed, again, a guess, the right formula for the spectral density of radiation from a black body. And here's the guess. But the spectral density still depends on the frequency to the third power out front. But now, instead of having a single exponential in the numerator, it looked like 1 over the same exponential minus 1. Okay? And for those of you who are mathematically inclined, it's actually very straightforward to expand this and see that it is proportional to temperature in the low-frequency regime. But of course, that's what Planck knew, and that's why he proposed this spectrum. Okay, so I presented these as formulas. Let me now show you what the difference really is when you plot it. Okay, here's the spectral density of radiation from a black body as a function of frequency, and then on the y-axis is in the intensity. Okay, so to the far right of the graph, we're thinking about high frequencies. So if you think about this as the spectrum of light, this is the blue end of the spectrum. If you go to the left, you're going to low frequencies, so this is the red end of the spectrum, if you think of, again, in terms of ordinary colors of light. What you can see here is that Wien's law and Planck's law agree extremely well in the high-frequency regime. This is why, of course, there was no difference and no crisis of experiment in the late 1890s. But if one was able to make very precise experimental measurements of the frequency of radiation, of the intensity of radiation at low frequencies, then you can see that there is, in fact, a difference between these two laws. Okay? And that's exactly what had happened in the year 1900 and why these different spectra were proposed. Now, you might look at this and say, well, they look pretty close. What's the big deal? Why would we care so much about this small difference? Again, it is exactly these small differences that inevitably lead to dramatic changes in what people think of as the physical laws that underlie the world. Well, Planck didn't merely guess his result. He was also a first-rate physicist, as you might guess, and he went on using standard thermodynamic arguments of the time, as well as a crucial step to attempt to derive the spectrum that he got out. The crucial step was to assume that in the black body itself there were oscillators, and what you're supposed to imagine, which he didn't really understand at the time, but what we now understand as is electrons somehow buried within the solid that would move around in some particular way. But the crucial fact was that these oscillators, Planck oscillators as they were called then, had their energy quantized. So this means that the energy levels, the amount of energy which they can emit was only in discrete lumps, not in a continuous spectrum. Okay. That was the crucial assumption for Planck to be able to derive the black body spectrum, which we now all know and love as the right spectrum for a black body. Okay, it was in this context, with all of this background, that then this character moved on the scene, okay, and started thinking about the problem. Well, Einstein was very familiar with this problem, with the Kirchhoff challenge and Planck's remarkable spectrum, the fact that it agreed with the experimental data to amazing accuracy, and he had no dispute with that. He was, however, somewhat troubled by the derivation in which Planck had used to arrive at his blackbody distribution formula. And of course, in sort of typical Einstein fashion, he decided to take a completely different perspective to try to analyze this problem and see what he could shake out of it. Okay. So here's what he did. He said, let me compare what happens when I have matter in a box, okay, a box of some volume, and then you let the volume expand a little bit, and then from that calculate the entropy associated with this system. Now, entropy was a well-known thermodynamic quantity out from the late 1800s, basically what we understand now as being a measure of the disorder of a system, okay? But it has a very well-defined mathematical meaning in thermodynamics. This was a completely well-defined problem to do, namely to take a box of, say, a gas, expand the volume a little bit, and calculate the entropy. You could go off to an experiment, do the same thing, they'd match, and you'd be happy. Let's suppose we do exactly the same thing, but for radiation, light. Put light in a box, okay? And then expand the box a little bit, and then calculate the entropy change as a result of expanding the volume. Again, it sounds esoteric, but this is how he approached the problem. Here's what he found. Okay. For matter, the change in the entropy went like the log of the ratio of the volumes raised to the power of the number of particles in the box, n, here. Okay. That was a standard result, well known. Okay, nothing new about that. When Einstein did the same thing with certain assumptions for radiation, he found that it also went like the log of the ratio of these volumes, but now raised to the power of the total energy in the box divided by the frequency of the radiation in the box, times a constant called Planck's constant. Don't worry about the constant. It was the striking similarity between this formula and this one, okay, that led him to make the following bold claim. Namely that light itself is quantized in particles, okay, not waves, in particles, with energy E equals h nu. And you can see from this formula up here that if each individual light particle has an energy E h nu, then this is basically just measuring the number of light particles within the box. Okay. That was the central conclusion from this 1905 paper. Now, let me try to illustrate the difference in approach to these two problems. Okay? Again, here's these sketches of what you're supposed to imagine with black bodies and with boxes of photons. Planck had imagined that the emission process that would lead to a black body spectrum was something that depended on the detailed properties of the black body itself, namely these oscillators. Okay? And Einstein, as I said, took a completely different approach and realized that actually light itself is quantized in different bits, in different pieces within the box. Later, in a 1906 paper, he actually showed that Planck's law automatically follows as a consequence of his law. So this was a more general result than what Planck had found. Now, this may seem, again, also sort of esoteric, and it may not even seem that revolutionary to us who we now have 100 years of history behind us. But at the time, this was a completely revolutionary idea. In fact, Einstein characterized this paper, the 1905 paper, as the most revolutionary paper he wrote that year. See, the problem was that until 1905, light was just strictly thought of as being a wave. Okay, a wave which is governed by, as Philip talked about, Maxwell's equations. And so they experienced all of the properties associated with a wave, namely diffraction and interference and such things. Okay? Particles, as they were understood in 1905, were understood to strictly not to diffract or interfere or have any of the properties of a wave. They just looked like particles. They wouldn't have this behavior. So Einstein's proposal to quantize light was actually counter to all of the classical intuition at the time. Okay? All right. So, well, in typical fashion, he of course didn't stop with just saying light's a particle. He said, well, what else do I get out of this idea? And this goes to the title of the paper, the title of the talk also, which is called the photoelectric effect. Okay? And the photoelectric effect was again, an experimental result that was gaining knowledge in the late 1800s and early 1900s, which was the following. They said experimentalists would shine light onto a metal and then measure the number and the energy of electrons that would be spit off this metal. Now remember, by this point, electrons had been discovered only about 3 years earlier by J.J. Thomson. But even by 1904, it was known that the energy of the energy of the electrons emitted from the metal was independent of the intensity of the light that you would shine on this. Okay, so if you had a light, you put more bulbs in front and you shone this on, you would see no difference in the energy of the electrons that came out. This was something that seemed extremely hard to understand from a wave perspective of light. Now, when you take Einstein's light quantum idea, this becomes an obvious consequence, because light is quantized in units that depend only on the frequency of the radiation. So just because you increase the intensity has no effect on the amount of energy that you can impart upon the electrons. The physical idea is that an individual light photon will come in and get absorbed by an electron and it pops out. So all that it depends on is the amount of energy that the electron has to begin with. That only depends on the frequency of the light that you're starting with. But then, so while this explained the data that had already been known at that time, it also predicted a relationship between the energy of electrons emitted versus the frequency of the radiation that you shine onto the metal. And here's the relationship. It's the most simplest relationship you can possibly imagine. Namely, it's just a straight line. Okay, here it is. The straight line has a slope determined by Planck's constant, and it has an offset, which basically is just the amount of energy you need to pop an electron out of the binding energy of the metal to begin with. Okay. So this was the prediction of the light quantum theory, this thing. This is what experimentalists now had to go out and measure and to see how well it would match data. Okay. I think it's very interesting to then ask the question, how did other physicists react to this idea? Unlike relativity and what you'll hear about in Brownian motion, physicists were very positive with these ideas in a very short order. But Einstein, as I emphasized before, was modifying the very nature of light itself and proposing that it was not a wave but particles. This was, not surprisingly, taken with some degree of skepticism. Here are a few quotes. Okay. So in 1907, von Lau had written to Einstein, von Lau, who got the Nobel in 1914, and said, I would like to tell you how pleased I am that you are giving up your light quantum theory, thinking that Einstein was going in this direction. 7 years after he proposed this idea, Sommerfeld said the idea that the quantum properties of emission and absorption should be transferred to light energy in space is audacious, and he wasn't being kind. Okay. And perhaps my favorite quote is one in which, when Einstein was being proposed for admission to the Prussian Academy in 1913 in Berlin, among others on the committee were Planck and other famous physicists of the day, and they had to write a report for the higher-ups to decide, well, do we take this guy for this institution? And in the report, they wrote the following two sentences. They said, there is hardly any great problem in modern physics to which Einstein has not made a remarkable contribution. Okay, sounds great. Then he may have missed the target in his speculations of light quanta, cannot really be held too much against him. Well, it took until 1915 when, hang on, there we go. It took until 1915 when Millikan had confirmed Einstein's equations. Millikan was an experimentalist. Did the experiments at Chicago, if I remember correctly, and in fact got the Nobel in 1923. But even Millikan, having measured the relationship between energy and frequency extremely well, he wrote in 1916 that despite the apparent complete success of Einstein's equation, the physical theory is found so untenable that Einstein himself must no longer hold to it. Okay. Well, to be fair, I think Millikan, while he may have been initially unconvinced by his own data, most other physicists, after his data had appeared, had pretty much adopted Einstein's view that light must also be quantized, just like these Planck oscillators. In fact, Einstein got awarded the 1921 Nobel Prize that specifically cited the work of the photoelectric effect. Okay. By 1925, experiments had already been getting better and better, as is typical in this field, And it was to the point where a physicist by the name of Compton was able to measure directly electron light scattering and do it to the level of individual electrons, individual particles of light, called photons, and that these individual scattering processes could be measured. You could measure the energy and momentum transfer, and that this behaved exactly as Einstein had predicted in 1905. So by this point, all of the skeptics had been silenced. Now you might say, okay, this is all fine and interesting. Light is a particle. I don't seem to realize that in everyday life. It looks like a wave to me. But actually, the practical applications of this idea are literally all around us. They're in this device here, okay, this laser pointer. The source of the light out of here is basically a light-emitting diode that functions largely based on the principles that Einstein had set forth from what is essentially an inverse photoelectric effect, explained 100 years ago. They're in the screen of the laptop computer. In fact, let me sort of conclude with the following sort of statement. Next time you see one of these, for example, stoplight with LEDs in it, or for that matter, you're looking at one of these computer screens, you might want to remember that this enormous legacy of Einstein in particular and physicists in general who go and explore these properties and all of this past and ongoing pursuit of the laws of nature. Okay, thank you.